industry are all very dependent on heat exchangers and the efficiency of it. If we just think of the renewable energy, here are two samples, the one of a solar thermal trough, in which the mirrors are being directed onto the center line tube here, and it is being heated, and that is actually also a heat exchanger. So my presentation outline today will be in three parts. The first part will be, I'm going to tell you a little bit more about our unique experimental setup, in which we did internal heat transfer convection experiments, which gave us very accurate measurements with a big database. Then I'm going to say something about modifications and perspectives required in internal forced convection literature. And now I'm going to show to you what we are teaching our students needs to be modified, and we need to rewrite some of the internal convection textbooks of our students. And in this regard, I'm going to present you a laminar chart, a flow regime chart, etc. And after that, I will make some conclusions. The next slide, please. Yeah, so this is the experimental setup that we've used. It has a test section with a power supply on, in which the tube is being heated. The heated water goes to a storage bath, which is connected to a thermal bath that keeps the temperature constant. And from here, it was possible to pump the water through one of three Coriolis mass flow measurement devices into a calming section before it went to the power supply. This test section is very important. The next slide, please. And the reason for that is that the test section, the type of inlet that can be used, has a huge influence on the flow characteristics near the transitional flow regime. It doesn't really make any influences in the laminar flow regime and in the turbulent flow regime, but it is of a significant importance in the transitional flow regime. And here are examples of 4 different types of inlets that can be used. The first one is called a square edge, where we've got a big calming section with a tube that is connected at 90 degrees to the calming section. And then the next one is what we call a re-entrant. And in this case, it goes into the calming section with a distance of approximately 1 diameter. Of course, you can also have re-entrances with 2 diameters and 3 diameters, etc. We just did experiments with 1 diameter. And then we get the bell mouth, which is typically as we get in wind tunnels. And the result of that is going to be a huge delay in the transition. And then the fourth type of inlet that we can have is an inlet that gives us a fully developed flow hydrodynamically before any heating starts. So this dotted line shows typically, and the red indicates the tube being heated, and on the blue, that is of course parts of the test section and the tube that is not being heated. And a lot of work has been done on this. Next slide, please, by Kajar and co-authors, and also at our laboratory at the University of Pretoria. And here is some results that typically shows the friction factors, how it is being influenced in the transitional flow regime. You see a blue line, a red line, and a green line, and those represent typically a re-entrant, a square edge, and a bell mouth type of inlet, and it shows at different heat fluxes how the transition varies. The one typically of the bell mouth, the transition only occurs not normally at about approximately 2,300 that the textbooks are showing us, but transition only occurs at a Reynolds number of approximately 8,000. So that is why the type of inlet is actually quite important the moment laminar experiments are being conducted, not for laminar Reynolds numbers, but close to the transitional flow regime, then they are very important. Next slide, please. So this is the test section that we've used. We used two different diameters test sections, a 4 millimeter and an 11.52 millimeters. And we had 27 thermocouple stations along the tube. Here in the beginning, they were spaced very closely towards each other, and then further away up to the last part, which was we knew we will have fully developed flow. The P1 to P9 shows all our pressure tap positions where we could measure the pressure drops. And at every one of these 27 thermocouple stations, we either had 3 or 4 thermocouples at the 0, 90 degree, 200, 180 and 270 degree positions in the radial direction. What is also very unique of our experimental study is the length to diameter ratios, which were in the order of magnitude of about 800 to almost 1,400. If we compare this to what has been done previously in literature, the longest ones in literature was about 400, or they were all shorter than 400 diameters. So our tube length was 2 to 3 times longer than that of what was done previously in the literature with the highest length to diameter ratios. Next slide, please. This is a summary of our experimental test matrix for the two tubes, the 11.5 and the 4 millimeters, and at different heat fluxes, at different Reynolds numbers, and all the mass flow rates that we've tested. In total, we did experiments with more than 1,000 mass flow rates, and we had approximately 90,000 temperature values at different stations. So these 90,000 is typically at a station, the average of the 3 or 4 thermocouples. So if you take into consideration the 3 to 4 thermocouples, then order of magnitude, we had about almost 300 to 400,000 temperature measurements. The pressure drops are, of course, much less. We had almost 3,000 pressure drop measurements. And with all that experimental data, it was possible for us to, at any point in the text section, determine the Nusselt number as a function of the Reynolds number, the Grashof-Prandtl numbers, and the position. Not only the Nusselt numbers, but also the friction factors. We also had some additional data that we got from Cooper, Shen, and Scotland from their articles. Very low numbers of data points, typically less than 100 from each. And then from our own lab, we also had some other students who also did some work with about another 500 experimental data points that was also used in our data reduction. The next slide, please. Now, if we look at internal forced convection, it is actually a very big and complicated field, and it is actually amazing that not a lot of work has been done in this field. So in the internal convection field, we can distinguish between laminar flow, turbulent flow, transitional flow, and also the quasi-turbulent flow regimes. And for every one of them, we can look at the flow, how it is, what the characteristics would be if they are fully developed or they are developing, and then also if the flow, the heat transfer is forced convection or mixed convection. And together with that, we can look at all the different types of inlets, which can be a re-entrant, a square edge, or a bowel mouth. We can look at different types of fluids, of Prandtl numbers of 1, smaller than 1 and larger than 1. We know if the Prandtl number is equal to 1, then the thermal boundary layer and the hydrodynamic boundary layer would meet at the same point, but it would be different for gases, typically of air, with Prandtl number of 0.7, while Prandtl numbers larger than 1, with water approximately 7, order of magnitude 10, but also with glycols where the Prandtl numbers can be up to 80 or something like that. Then also the orientation of the tube can play a big role in terms of it being horizontal or vertical, and if the flow is going upwards or downwards. And then lastly, we can also look at the correlation between heat transfer and pressure drop data. So what we did over the past 10 years is we looked specifically at the laminar and transitional flow regimes, a part of the turbulent flow regime, as well as the relationship between pressure drop and heat transfer. The next slide, please. Okay, so let's start with some of the basics that we teach all our students. In the turbulent flow regime, we introduce them to the Dietersen-Boelter equation, the Kolben equation, the Siller and Tate, the Petkov and Glinsky equations. Now, this was obviously great work that these pioneers did, but the reality is it was done about 70 to 80 years ago. And at that stage, they didn't have the good instrumentation we had today. And if we go and plot typically for water with a Prandtl number of 7, the Nusselt numbers as a function of Reynolds numbers, then there's approximately a 34% deviation in the results. The next slide, please. And which is a little bit problematic because these days, you know, we are not really that satisfied if we can develop correlations with errors of about 30%. These days, we would like to move towards at least 20% and preferably less than 10%. And what you can see in literature is everywhere where people would do some validation experiments, then the one person would choose Glinsky and the next one would choose Kolben, etc. And the reason for the choice is normally they look at which one of those equations would be the closest to the experimental data. So it is really actually not clear which one of those correlations are the best. Normally it is assumed because the Glinsky equation was developed, the last one, which was the Glinsky equation, that one will be the most accurate. However, that's not the case, and I'm going to show it to you just now. In terms of, except for our experimental data that we had, we also went back to literature and we did go and look when Glinsky, for example, got his data from and from whom he got it. And here we can see typically, who did some of the earliest experiments and the number of data points that was available. So in these databases, for example, the Sherwood and Petrie one, for water, there would be about 131 experimental data points, which are orders of magnitude less than the experimental data points that we had. Next slide, please. So what was different from our database is that, except that we had a large database was that 90% of our data, 95% of our data had uncertainties of less than 5%. So it gave us the opportunity to make very good comparisons with what was done previously in literature and to identify which ones of those equations were actually the most accurate. And it also gave us the opportunity to revise these equations so that we can have a more accurate equation. Next slide, please. Thank you. So here we can see where we have compared with this study, this is the 3 columns here on the left, this study with that of Colburn and Sitter and Tate, etc. And here we can see plus or minus 10%. So we have found that, for example, the Glinsky equation, just 70% of the data would be within the 10% error mark. And what is actually interesting is that it shows that the Colburn equation is actually more accurate because it had 74% of the data was within 10%. However, if we look at plus or minus 20%, then only then about 99% of the data is accurate. So if we look at this critically, it actually looks as if the Colburn equation is actually more accurate than that of the Glinsky. Okay, next slide, please. There you go. Okay, so this is all our experimental data that we've used. And the result of that was that we could develop a modified equation. We learned from the Glinsky and the Petukov equations in terms of this term, where we rather plot the results of Reynolds number minus 500. And it was then possible for us to have this very good correlation with an R-square value of 0.999. And the result of that was that we could develop a new, more improved equation that can be used for turbulent flow with an average deviation of just 4%, which is within the 5% uncertainty of all our experimental data. Here you can also see we did the experiments from approximately Reynolds numbers of 10,000 up to hundreds of thousands. Here at the end, it looks as if the deviations are getting bigger. Here, at the end, when you look at the green data points and together with the red and the black ones, but that is just because of the logarithmic scale. So that's the only reason why it looks as if the green data is falling away very sharply from the black line. Now, this disadvantage of this very accurate equation of us is that it takes a little bit more work for a student to calculate the Nusselt number very quickly, and especially for a student like me, who is very lazy. I wouldn't like to do that, except if I have put it somewhere already on an Excel spreadsheet and already debugged it previously. So I wouldn't like to do that. But if you don't want to do it like me, then you can use this bottom equation, which just says the Nusselt number is equal to 0.13 multiplied by the Reynolds to the 0.867 multiplied by the Prandtl number. And that would, the average deviation of that equation is 6%. So it is still very close to the uncertainty of our experiments, which was 5%. So I myself, if I need to do a quick calculation, would prefer to use that equation. Next slide, please. Okay, now with improved equation for turbulent flow, we would of course prefer not to have an equation for turbulent flow, for laminar flow forced convection, for laminar flow mixed convection, and the transitional flow regime. However, such an equation can be developed, and we did that. And here are some of the details, and it is available in our previous articles. I will show you the articles on the last page of my presentation. It looks very complicated, and yes, it is unfortunately very complicated if we want only one equation, which can be used for laminar flow up to turbulent, and an equation where you just need to put in the Reynolds number and the Prandtl number, and it will do the rest for you. So such equations are available, or that we've developed. And next slide, please. One of the challenges that we also had is that in the transitional flow regime, this is typically what happens, where the Reynolds number increases from low Reynolds numbers to high Reynolds numbers, we get these almost discontinuities. But the challenge is that different authors would look at these points and they would use their own discretions in terms of where does the transition start. And that is not something that we would like to do. We would rather like to have an objective criteria for defining where the transition starts and when it ends. And we've developed such criteria. And the next slide, please. Okay. So this is typically some of the nomenclature that we've developed. I'm not going to spend a lot of time on it, but here we can see typically how the Nusselt number changes as a function of Reynolds number in the laminar flow regime, the transitional, and the turbulent flow regime. And next slide, please. And at all three of those red points, we would actually like to be able to calculate it from our data, so that when different people would look at it, would not have different values where the flow changes from where the transition starts, where it ends, and where is the end of the quasi-turbulent flow regime. So we've developed these criteria which can be used to calculate it with. And we used, for example, I'm not going to go into the detail, but the transition gradient, which is that gradient there. And you can actually see to define that point there where the transition actually starts, you can use that line to do it with. However, the J factor line has a much sharper point there, and it is much easier to calculate it from the J factors. So in some cases, we used the Nusselt number data, and other cases, we used the J factor data. And with that, it made it possible for us to define new nomenclature, such as the transition gradient, the width of gradient, the starting point of transition, the ending point, etc., etc. Again, more information is available in our articles. Next presentation, next slide, please. Okay, just coming back to what we teach our students on forced convection. As you all know, the hydrodynamic boundary layer and the thermal boundary layer, and how the heat transfer coefficients, the friction factors go through the developing part of the flow until the flow is fully developed. And typically we teach our students that it would take the hydrodynamic boundary layer, the thermal boundary layer. We can calculate the length of that, which is equal to 0.05 Reynolds multiplied by diameter. And the thermal one is, that length is if we multiply it by the Prandtl number. Next slide, please. However, these coefficients of 0.05 in some other textbooks actually gave different values, but most textbooks would give this value of 0.05. That actually comes from theoretical work, and we did go and check that with our experiments. Next slide, please. And we have found that that value is actually very inaccurate. We have found that that value should be 0.12, which means it is more than double what we are teaching our students. Next slide, please. Here is the raw data in which we can use to convince you that our prediction of the C value should actually be 0.12. Next slide, please. I'm not going to go into too much detail of that. Yeah, so it shows that a value of 0.12, only 80% of our experiments were within 5% from the Nusselt number, equal to 4.36. If you want to be 100% sure, then rather use a C value of 0.14 and not 0.05. Next slide, please. Okay, so if you start doing experiments, good experiments in the laminar and transitional flow regime, we have found that some things that we are teaching our students is not correct, or almost never. And that is that forced convection occurs and that the Nusselt number is either 4.36 for constant heat flux or constant wall temperature 3.67. Well, we have to teach our students that that almost never happens. I'm going to show it to you now. Then the flow is almost never forced convection, but it is always mixed convection, and that there's a huge distinction between the different flow regimes in the laminar flow regime. Next slide, please. So what we should actually teach, or what we do teach our students, if you look at the Nusselt number as a function of the tube length, is that the red line shows how the Nusselt numbers should change from very large at the inlet up to a value of 4.36, and the distance would be 0.05. Now, I already showed to you this distance of 0.05 should be 0.12. So that is what happens. But that happens, next slide, please, for only forced convection conditions. And that actually almost never happens. It only happens in capillary tubes or mini channels, or in the situation where there's zero gravity, and in very, very carefully planned experiments with extremely low heat fluxes and very, very long tubes that we have tested in our laboratory. Next slide, please. So again, going back to what we teach our students here, we should be more careful, and we should bring it to their attention that all this gives us a good fundamental understanding. What we're showing to our students here almost never happens. Next slide, please. What do happen, of course, and this is not that we have discovered it, this has been known for a long, long time, is that there would be secondary flow. And the secondary flow is because of the buoyancy effects. You get the secondary flow, and the result is that in most cases, where tubes are being heated or cooled, the Nusselt number would not be 4.36. It will not be forced convection. It will be mixed convection. So typically, we will get the results in red, which can be about 300% higher than that of forced convection. Next slide, please. So what will happen is not the red line for forced convection, but actually the green line. That is actually what will happen in most cases. So the green line would follow this red line of forced convection. Then it breaks away there. Why does it break away? Because of the secondary flow changes the thickness of the boundary layer that was developing. The secondary flow would start, it would develop up to the point where it is fully developed. Next slide, please. The next slide, please. There you go. So this can also be checked with CFD results, and here are some of the work that was done, that we did do, showing the CFD results very nicely. Next slide, please. But with the result of this work, we typically, so this green line is the green line that I showed you previously. If you would go and increase the heat flux, then the line would typically follow this yellowish line. So it shows that the results is a function of the Grashof number. So this is very low Grashof numbers in red, up to the yellow value, which is the highest Grashof number. And when we started plotting these results, we actually realized that there should be some more nomenclature that should be developed. We've got three different flow regimes. We've got the forced convection developing flow regime, a mixed convection developing flow regime, and then the fully developed flow regime. And these lines, this line here, would actually shows us where does these changes occur from the different flow regimes. Next slide, please. We have also found that there's an excellent relationship between the pressure drop and heat transfer, which can be determined with these correlations, and that the relationship, like the Kolben analogy, is not only valid for one flow regime, but it is actually valid for all flow regimes. It is just in the laminar flow regime, the Grashof number needs to be taken into consideration, as we've got here in this red block, while in the green block shows us more the transitional flow regime and the turbulent flow regime, and it shows to us that the Grashof number plays no role. Next slide, please. Well, we all know of the Matthias and Eckert flow regime maps as the one that, as well as the one that was developed by Professor Gajar and his student Tom. And these were their maps that indicates the different flow regimes. We've tested it with our data, but unfortunately we found that they were not very accurate. These maps were also developed with a very, very limited number of data points. For example, this map of Tom et al. Was just developed with 50 data points. Next slide, please. So with our data points, with our 90,000 data points, it was actually possible for us to develop new flow regime maps, which looks like this. If we look at the map here on the left-hand side, it shows the Reynolds number as a function of a Rayleigh number. And we have different flow regimes. Everything in dark blue is forced convection, while everything in red is mixed convection. So it shows actually how the transition occurs from forced convection to mixed convection in the laminar flow regime, the transitional flow regime, and the Reynolds in the turbulent flow regimes. If you don't like to work with a Rayleigh number, you can work with a modified Rayleigh number. So, however, these maps was for the fully developed part of the flow regime. The next slide, please. So, for example, if you're interested, again, I want to emphasize in the fully developed flow regime, if you would like to know at the Reynolds number of 1,000 and a Rayleigh number of 1,000,000, there, at that point there, with that white star, what the Nusselt number would be, then you can look at that color and you can see it is actually 3.5, which means that if you take the 3.5 multiplied by the forced convection value of 4.36, then you will get the correct Nusselt number, which is 15.3. Next slide, please. However, if you're interested in the developing part of the flow regimes, the next slide, please. I'm still waiting for the next slide, please. My presentation disappeared. Ladies and gentlemen, I'm not sure if you can still hear me, but I am at the end of my presentation in any case. So I just wanted to show you that in the developing part of the flow regime, how you can determine the Nusselt numbers. And then I wanted to conclude some of the most important results. And then in the last slide shows to you the 5 articles that we've published, in case you would like some more details. I'm not sure if everybody could hear me, but Dr. Kondo, thank you very much. I'm at the end of my presentation. I don't know if there's still time for questions, but I hope there are. But ladies and gentlemen, my apologies again for the problems we had sharing my screen. I hope it will not happen in the future. Thank you very much.
Thank you, sir. Thank you very much. If anyone asked any question, please. There is a little bit problem with the internet connection.
Okay.
Is there any question?
Professor Mayor, thank you for your presentation and very enlightening presentation in this fundamental subject. So I would like to ask you one question, that you have seen so many equations and a nice regime transition and the proper correlation to get less error because you have done a lot of experiments. Now my question is, sir, for a given heat flux,
Okay.
or a given temperature,
Yeah.
and if I know the flow condition, say my inlet flow condition is known, all the geometric parameters are known, temperatures or boundary conditions are known. So is it possible to accurately predict the heat transfer coefficient, including the effect of natural convection or including the effect of mixed convection? Is it possible to get a single equation without any ambiguity? Maybe there may be error, but maybe some
Yeah.
uncertainty. Is it
Yeah.
possible?
Yes, it is possible, and that is what we did. So we did do the experiments for different heat fluxes, and there is an equation that I showed to you on one of the slides that actually that you can use for any Reynolds number. So it's really a case of just you need to know what is your Reynolds number, the Prandtl number, and the Grashof number, or the modified Grashof number, so the heat flux. And with that, taken that into consideration, that very long equation of mine can be used, and it will be within 10%, even in the transitional flow regime. So the equation is quite accurate. Yes. So it was in our publications.
Hello, Professor Mayor. I have a query on this one. It's
Yes.
definitely a very beautiful and nice presentation. So, sir, I would like to know what is the application of this area of work?
Well, the application is in heat exchangers, and heat exchangers, of course, are directly involved in the efficiency of thermal management. So that is the first answer. And the second answer is that heat exchangers, that as I've showed to you, which is just a simple circular tube, is the easiest type of heat exchanger we get. Normally, the geometries of heat exchangers are more complicated. However, for us to understand what happens in more complicated heat exchangers, we first need to understand the fundamentals in terms of what happens in heat exchangers, which are very simple in geometry, like a circular tube, and typically what happens in them. Because the fundamentals that I've showed to you in terms of how long the flow takes to fully develop, and or if the flow is forced convection or mixed convection, will be relevant to them also. But it's not the right thing from a scientific point of view to start with the most complicated type of heat exchanger with a very, very complicated geometries and try to understand it for those heat exchangers while we do not understand it for the most simplest type of heat exchanger. So this is the work that I've showed to you is very important for the foundations of our undergraduate students and our postgraduate students who in the areas of the thermal sciences, the heat transfer, and the thermodynamics.
So
Thank you very
thank you,
much
sir.
for the equation.
But I would like to add some one more point, whether this idea is actually been applied for some experimental work in experimental modeling of his heat exchanger.
I beg your pardon, I couldn't hear.
Now, whether this study or this concept has been applied actually in some experimental modeling of formation of
Yes,
this heat exchanger.
yes, it did. We, of course, ourselves did the experiments. And then I actually already had a postdoc from India who was simulating that for our circular tube, and another student who are also busy um, taking some similar experiments for the plate heat exchanger.
Okay, thank you, sir.
Yes, please. Okay, sir. Thank you very much, sir.
Thank you very much, Dr.
For your beautiful presentation. Thank you very much, sir.
It's my pleasure, and thank you very much, and greetings from South Africa. It was nice talking to you this morning. Thank you very much, everybody, and bye-bye.
Bye, sir. Bye, sir. Thank you very much, sir. Bye. Our next keynote is Professor Kaushik Ghosh from Jadavpur University. Sir, please start, sir.
Yes.
Thank you.
Yes. Am I audible?
Yes, sir.
Good morning, all. Actually, at the very beginning, I would like to express my thanks and regards to the organizers of this conference, this ICTEMA 2020, which is being held in Jalpaiguri Government Engineering College. And I would like to express my regards to the principal, Professor Omitavo Ray, and Dr. Gautam Kumar Panda, who gave the inaugural address. And I would like to express my my thanks and good wishes to the all plenary speakers, particularly Professor Mayer for his enlightening speech. Also to Professor Suman Chakraborty, an eminent researcher in the field of microfluidics and biomedical engineering. Professor P.K. Dunn, who is another keynote speaker, and it's my honor. Actually, I feel really honored to be invited to deliver the keynote speech in this occasion. Particularly, my feelings is at a high level because I am an alumni of this college. I spent my 4 years in this college. So some of the teachers are still present. I would like to express my regards towards Professor Subrato Bhattacharya and other faculty members, Professor Sopan Moitro, Professor Asim Mahapatra, and other faculty members. And I would like to express my good wishes to all the participants, different faculty members from different colleges, the young researchers who will be presenting here, their effort of research. So I would like to particularly thank Dr. Arijit Kundu and Muhammad Naeem Hassan for inviting me. So today in this occasion, let me briefly talk about some topic on boiling heat and mass transfer problems. So I will discuss about these few challenges related to practical boiling heat and mass transfer. And here you know this as the topic is related to thermal engineering. So it's a complex problem. This boiling heat and mass transfer is a really complex problem and has many practical applications. And we had some challenges to solve this kind of problem. How we solved, I will discuss a little bit about some of the techniques, and I will discuss about some of the results and how it helps in the community in the practical engineering field. That I will also discuss. So first, let me just highlight the researchers who are involved in this work. So I essentially work in a group. So you can see here these professors, Professor Achinta Mukhopadhyay, Professor Swarnendu Sen, Professor Dipankar Sanal, and Professor Nirmal Kumar Manna, who are involved in this work. Okay, and we have some collaborations also. Dev Mukhopadhyay from Bhabha Atomic Research Center, Renaud Meno from IRSN France. So actually I spent 1 year in France for some postdoctoral work, research work in this field. And more important, or the most important part, these 4 fellows, Dr. Pallab Sinha Mahapatro, our ex-student, who is currently assistant professor in IIT Madras in Mechanical Engineering Department. So who did a lot of work, Dr. Deepak Chandra Das, who is now in NIT Agartala, he is also involved in this kind of research. Dr. Arannok Chakraborty, who is assistant professor in Jadavpur University, he is also past researcher in this area, boiling heat transfer. And Dr. Priyankan Dotto, he is also a PhD. He was a PhD scholar, now a research associate in University College London. So this is the effort of many people, but most of the efforts or the work has been carried out by our research scholars. So we gave different kind of guidance, inputs to them, and they have executed this work. So we have the funding agencies who have supported this work. One is Bhabha Atomic Research Center, Mumbai, then Board of Research in Nuclear Science, India, CSIR India, who provided fellowship, and DST Inspire, who provided fellowship to one of our students. And there is a Areva fellowship of France, which is now turned into this Framatome company. So this is some industrial funding was also given for the providing the fellowship of one of the scholars. So now let me discuss about this problem. So basically I will first discuss about 2 of the application first. Okay, so this is related to severe accident situation in a nuclear reactor. So what is that? So you are aware of Chernobyl accident, or you are aware of 3 Mile accident, or latest the Fukushima accident. You know, all these nuclear accidents occurred due to many safety failure. And one of the safety failure is the basically due to the failure of some components, the decay heat, the reactor is stripped. Even the reactor is stripped, there is a core meltdown. Core meltdown means the core consists of the fissile material which is generating a large amount of heat, and it will still produce heat because of the decay heat, you know, decay heat effect of the radioactivity. So due to that, if there is some loss of coolant, you know, the coolant failure is there, the pump doesn't work, or some other safety devices do not work. So due to that, there will be the molten corium. Corium means it's a material which is a mixture of uranium and the other materials, uranium and say zircaloy. So this molten corium, this undergoes melting because the fuels undergo melting due to the loss of coolant, and this fuel element after melting, it falls in the reactor vessel. So there will be some coolant. So during the fall, it will undergo the fragmentation into small particles. So it produces intense vapor, and here lies the boiling heat transfer. Because of very high temperature, very high heat flux, there is a huge void generation and vapor generation. Due to the vapor generation, there will be a pressure build up, and moreover the hydrogen may be produced, so there may be a failure of the reactor vessel. In fact, that is the possible reason failure of Chernobyl. That is another possible failure in Fukushima also took place in this way. So this is a very dangerous situation, and to mitigate this, we need to understand the process, and we have to take the proper measure how to provide the better cooling under this boiling situation, a very high heat transfer situation, and under this boiling a huge vapor build up. So what is the how much vapor is produced, okay, due to intense boiling? That is also an issue. So this phenomena is called molten fuel coolant interaction or molten particle coolant interaction. So there is the melt pool is there, and it gets later it gets solidified here. It forms a bed, a debris bed. This is called a debris bed. Now this is debris bed may be in the safe state because it is coolable, but it may not be coolable. Again, if there is some safety failure, it may not be it may be non-coolable, and there may be containment failure, and there will be spread of radioactivity. So I am giving you one typical example of this boiling, practical boiling heat transfer. So we carried out several projects on this area, and there are some works have been done in this by our group. So I would first discuss about the film boiling issue. What is film boiling? Because of these particles under high temperature, you know, if a particle or surface is having a high temperature, this produces a stable vapor film, and from the vapor films the bubbles are generated, and this stable vapor film configuration is called film boiling. It is made of two-phase boundary layer, and it is a very complex problem because there is involvement of phase change. There is several instabilities due to the liquid vapor complex interface. There may be radiation heat transfer and the other heat transfer, convective heat transfer, and the phase change effect is there, and it may consist of complex flow regime. Flow regime means, you know, there may be a complex two-phase flow regime. There may be bubbly flow, there may be dispersed flow, there may be annular flow, there may be crispy annular flow, and there may be, you know, slug flow. So these are very complex flow regime, and moreover, to implement this in the system code, in a multi-phase CFD code, that is also a big challenge. So there are several challenges involved in studies related to film boiling, and there is an application area in heat treatment and nuclear safety. I already given the example that in the nuclear field, it is a very important area where it finds the application. So to solve this, we have there are several challenges, and we have solved this in this way. So first, to understand the fundamental principle of film boiling. Okay, fundamental principle. What is the physics involved, and what are the processes involved in a simple geometry. So we have considered a simple geometry, a plate geometry, a spherical geometry, and we developed two rigorous model. One is integral model, is a more involved model, and another is scaling analysis. Scaling analysis is something, you know, you identify the proper scale of the problem, and you know, you have, if you go through the book of Bejan, convective heat transfer by Bejan, there you will find the scaling analysis is given. So you know, it's kind of order of magnitude analysis, and you have to identify the proper scale. And in this film boiling heat transfer, there is a high superheat case, there may be a low superheat case. You know, as you have seen the lecture of Professor Mayer, you can see that there may be mixed convection, there may be natural convection, there may be forced convection, there may be a high subcooling, there may be low subcooling. So there are different situations may arise. So we have categorized into these different pattern, and we have done a particular scaling analysis. Now in the length scales also there are several issues. As you can see, there are interaction of multiple phase like liquid phase and vapor phase, and the interaction between two phases, and there is a mass transfer from liquid to vapor due to high temperature and phase change. So this mass transfer makes this length scale more complicated. So there is a capillary wavelength, and there is Kelvin-Helmholtz instability, and there is a criteria called film Reynolds number. When the film Reynolds number increases to beyond a particular value, there may be an instability. And so with this we did some regression analysis, and from this scaling analysis and integral model we have developed several correlation, and these correlations are validated with experimental result. This is the first step, that to understand the process in the fundamental level. You take a simple geometry, analyze it, see the proper physics, take the results and compare with the experimental data. You see whether the error is minimized, and once this part is achieved, you implement it in a CFD code system level. Why system level? To analyze this kind of situation, when there are many particles, and these particles are undergoing fragmentation. Due to fragmentation, these many particles interaction with the liquid, there will be a tremendous vapor generation. So this is a system level. So now we are first attacking the problem at the unit level, when we are considering a particular fragment or a spherical particle. Then we develop the correlation. After developing correlation, we integrate in a CFD code. CFD code means we are now modeling the system level. That is the strategy we have taken in solving this kind of problem. Okay. So we have developed a multi-phase CFD code PNAC. Using commercial code, Fluent or ANSYS Fluent or this kind of code, it is very difficult to solve this kind of problem. There are dedicated codes like MC3D in France, and PM Alpha in other country like in US, and some other codes are there. Some 5-6 codes exist in world, but these codes have been developed after effort of 10 to 20 years in different countries, and dedicated researchers have worked to develop this code. So in our group we have developed a CFD code called PNAC with collaboration with BARC. This was funded by BRC project. Several BRC projects were given. So this is the strategy, that after developing the unit model, you go for implementation in the CFD code. Okay. So this is the problem geometry of the unit model, this plate geometry and the spherical geometry, and you can see that there is a vapor layer. There is a vapor layer, thin vapor layer in the film boiling configuration. There is a liquid layer. Okay. So in the sphere also you find the vapor layer, liquid layer. There is a thermal boundary layer and a hydrodynamic boundary layer in the liquid, and in the vapor there is a single layer. So basically it is a two-phase boundary layer problem. You can see in the single phase boundary layer, there is a thermal boundary layer and the hydrodynamic boundary layer, but here there are two phase. One is vapor phase, another is liquid phase boundary layer. Now you can see some of these integral results. You can see the comparison of our integral heat transfer result from the integral model with the experiment, and you can see there are fair agreement, and the scale analysis results you can see by comparison with several researchers. You can see that the correlation developed by our model for several situations, all these situations, high superheat, low superheat, mixed convection, natural convection, all these data are coupled. And you can see these data we have developed, whatever from the 5 set of researchers we have correlated in our correlation, and you can see this is within the 20% plus minus band. Considering this complexity of the problem, this error is not a huge error, we can say. And you can see these data which we have got. This is for the sphere. So these are the plate unit model and the spherical unit models. Our data matches well with the experimental data, and now we integrate in the system level code. In the system level code means what we are doing here, there are some particles. You can see some particles. These particles are moving in the downward direction. How these are dispersed? Because how these are dispersed, if we can identify, then we can identify the interaction zone between the particles and the liquid, and how much vapor is produced around that. So to simulate that, we have modeled here that the vessel here, and it contains some liquid, and we are releasing some particles from the above. And first we do in the system level some small scale experiments also we have done. We are not going into detail of the experiments, and we have compared the particle under isothermal condition first. This is cold premixing. you can see these experiments, these experiments, you can see the experimental image. It was the images were from the camera, first high speed camera, and these are the CFD simulation in the particle in the our PINAC code gives the CFD simulation like this. This is the particle spread, how the particles are spreading inside the liquid, and this is the image from the experiment. This is the image from the experiment at different. This is the 192 millisecond. This is 222 millisecond, and you can see the penetration of the particles with time. How our numerical model is going in the experiment. You can see the fair match between our system level model and the experimental model. Okay. You can we have compared our data with several experimental data. This Chaos 08, Magico, these experiments have been performed by several groups in the nuclear industry in different countries. Okay. So these are the standard experiments or standard programs carried out internationally. So this PINAC code performs well. You can see our code performance, the results of the code of the penetration of the particles, how it is varying, and you can see the dispersion and penetration level, how it is varying with the time, and you can see the well match with the experimental value and our model CFD model data. Okay. So here now the next problem you can see here, these the particles are falling. So this is the particles, the blacks are particles, and you can see the fragmentation is also modeled here. So fragmentation is due to the several modes. There is a Rayleigh-Taylor instability, there is Kelvin-Helmholtz instability, and there may be a boundary layer stripping. So these particles, since these are molten particles, these particles undergo further fragmentation. Due to fragmentation and increase in the surface area, the vapor generation will be more intense, and you can see these are the vapor bubbles which are generated under film boiling condition, and these bubbles are moving in the upward direction, particles are moving in the downward direction, and the vapor void build up. This is a one vital parameter in this field to predict this, and very less data is there in this area. So we have developed our code, and we have seen, let's see, this film boiling model, how we have implemented in our CFD code. So you can see this from the particle, the vapor film is produced, and this vapor film is growing, and there is a necking. From this necking, these bubbles are detached here, and these bubbles are moving in the upward direction, the particles are moving in the downward direction. And you can see under this configuration there may be different flow regime. I have already discussed this flow regime is a big issue, big and complex issue. So this is the film bubbly flow where the void fraction is less than 0.3. You can see these particles, and the liquid is continuous, and there are vapor bubbles. So this is bubbly flow, and you can see the droplet flow where there is a vapor is continuous. The vapor is continuous, and there are some liquid particles out of it, and these are the black are the solid particles. Okay, so there may be transition flow also. So these, depending upon this flow, the heat transfer characteristics and the drag characteristics, all these change, and these are implemented depending upon the flow regime demarcation. This is employed in the code. Okay. Now you can see the void build-up under film boiling condition, how it is changing with the time. Okay. So you can see in the void build-up with the time how much void is produced, and this void we can see this is the experimental data, and this is the prediction of the PM alpha code, which is an USA code. This is a VAPEX code, another code by some Korean community, and actually this is our code present simulation. So this is well within some margin. This is approaching the experimental data. Okay. So you can see there are some obstruction in this field. Okay, so obstructions, why we have simulated the obstruction? Because Indian pressurized heavy water reactors are some channels or obstruction. So under obstructions, how the particles are, if some particles fall, how these obstructions influence the flow pattern, the particle penetration, the vapor bubble generation. Okay, how these are influenced. To model this, we have modeled here single obstruction, and you can see the the particle, how these particles are falling here, and these are changing due to this obstruction, how these are shifted in this direction. And if we use the multiple obstruction, this is how the particle falls. Okay, and you can see the influence of subcooling. Say if we increase the subcooling from 3 to 10K, you can see the void buildup is very less. Under saturated condition, this is 55% of void is produced, and if we use the 10% subcooling, we are getting some 15% kind of void. Okay, so you can see with that subcooling of 10 degree can reduce the void to a great extent, which we have simulated from the system level code. Okay, so from this particular work, what we have discussed, the film boiling work, there are several publications we have done in journals. Okay, you can see these publications we have made. Okay, and the first authors are highlighted because you know their contribution is the maximum. Okay, and the book chapters, we have 2 book chapters in this area. This is the area of film boiling research, the first one. And now we are going to the second part of this problem. You can see we have already discussed in the second part what happened. Now say fuel coolant interaction stops, okay, or it is ended. Now say this melt pool settles inside in the floor, in the reactor floor, and you can, there is a porous bed, debris bed is formed. Now an issue is that you again, due to decay heat, this porous bed will keep on generating heat. Now we need to cool this. If we don't cool it, it will keep on generating heat and it may undergo remelting under critical heat flux condition. And then if it undergoes remelting, it may penetrate the floor, and then the radioactivity, there may be release of radioactivity. So we need to cool this porous bed, and this is called debris bed. So debris cooling is another issue, and Dr. Aranav Chakraborty has carried out this work. Okay, so you can see how we have solved this problem and what are the challenges. So here one issue is dry out estimation. What is dry out? You can see, say if this is the debris bed part and there is a water pool is there and it is generating heat. So what happens? This vapor, whatever is generated from here due to the action of the liquid and the heated bed, when the vapor is generated, vapor will try to move in the upward direction, and due to the lower density and due to the higher density, the liquid water will fall downward. So there you can see there is a counter current flow kind of thing. Now due to the presence of this porous bed whose resistance is very high, there may be accumulation. You can see the accumulation of vapor here. Now if the vapor is accumulated inside the bed, what happens? This bed thermal conductivity, you know, due to the lower thermal conductivity of the vapor, it will be devoid of the coolant. Now if the bed is devoid of the coolant, it will undergo remelting and it will undergo that. So this is called dry out condition. So now for this debris bed, the paramount importance is to estimate the dry out heat flux. So there may be top flooding condition, there may be bottom flooding condition. Okay, and there may be lateral flooding. Okay, so top flooding means if there is a debris bed, you flood the bed to cool from the top, and bottom flood means you try to flood to cool the bed, you try to flood from the bottom, and laterally you are trying to cool it. Okay, so how the bed dry out is influenced by all these situations. Okay, moreover, how several parameters influence, like system pressure, bed composition, coolant subcooling, bed structure. Okay, now bed structure is another issue. What is the bed structure? You can see several experiments have been done, and you can see this porous bed is formed like a heap like structure. So this is basically nuclear waste, debris, corium. Okay, so we have done also some in-house experiment. How we have done the in-house experiment? We have taken some molten tin or molten lead or molten wood metal. This molten wood metal we have put in the furnace, in the top furnace. So this molten metal is released from the top, and inside we have put some liquid, and we have seen, as you can see here, this is a heap like structure is formed. Okay, so now we have seen this work has not been done by anybody, because other researchers, because all have taken the bed in a rectangular structure or the cylindrical structure. But what we have done here, in this case, debris bed, this debris bed is basically formed in a heap like structure. So we have simulated it with a truncated bed. Okay, truncated bed. Now here the strategy is, we have not used any dedicated code. We have tried it that why not using some ANSYS Fluent. There was no report of work using any ANSYS Fluent or commercial software, because all have used some dedicated software or developed indigenous software. This is the first work we have published that using Fluent debris bed problem, which is a very complex problem, we have implemented some UDF. These UDFs are employed a very clever work of Dr. Arannok Chakraborty, that he has implemented all complex closure relation and UDF in the Fluent platform, which is not an easy task. And then the phase change of liquid water into vapor, this boiling heat transfer, which is a very challenging thing. So he has implemented ANSYS Fluent, and he has successfully validated with the experiments, and he has come up with the important results. So to achieve this, he has first solved single phase natural convection, single phase mixed convection, and the multi-phase flow, where liquid vapor dry out prediction, and the effect of bed composition, how the particle diameters influence, how the bed porosity influence, how the bed structure influence, how the liquid subcooling influences the dry out heat flux and the remelting issue, and the flooding mode, system pressure. All these aspects have been checked, okay, to estimate the dry out heat flux, and to see the, moreover, the dry out mechanism also he has solved, how the dry out point shifts from the situation to situation inside the bed. That also has been solved by Dr. Chakraborty. Okay, so here you can see this is a single phase natural and mixed convection. This is single phase, and we have seen the validation of the temperature with the location, and you can see the Nusselt number prediction with the comparison of the experimental data. And this, since this is a numerical work, the grid independent study is required. So all this he has done using ANSYS Fluent and using the UDF. Okay, so here also he has done some single phase mixed convection, and you can see some of the validation here, the comparison of the results, the CFD results with the practical data. Okay, and you can see some of the single phase mixed convection result, the effect of Darcy number. Since it is a porous bed, the non-dimensional number is the Darcy number, and there is a flow spreading effect which is observed, as you can see here, flow spreading effect, and the weakening fluid flow in the porous media. Since due to the huge resistance, the flow is less here, and flow is surrounded in this part. This is the clear fluid part, liquid part, and this is the bed part. So there is a very complex situation. Due to this porous bed, inside the resistance is high. Okay, so you can see the streamline and isotherm and energy flux vector pattern from here, and you can see the velocity pattern. You see the velocity, typically inside the bed the velocity is less, but outside the bed in the clear fluid part the velocity is very high. Now in the multi-phase flow, which is the boiling part is involved here, you can see the different kind of bed is considered. Okay, so one is this kind of bed, one is the space for lateral flooding, how the lateral flooding influences, then this kind of bed, this conical bed, and the truncated conical bed, the cylindrical bed. All these beds have been simulated by using this development of this model. Okay, so you can see again, I have already discussed that the flow regime is a big challenge. So this flow regime, this is the bubbly flow, liquid and vapor bubble, which is generated inside the bed and outside the bed also. So there may be liquid droplets, vapor. So bubbly and vapor continuous droplet flow, these all are implemented inside the CFD code. And interfacial drag, which is a very huge issue, because this is a two-phase drag. You can imagine there is a liquid vapor mixture is rushing, and the drag is basically the two-phase drag. Okay, so this two-phase drag is implemented inside the model. Moreover, the heat transfer, boiling heat transfer, which is a very challenging thing. You can see the nucleate boiling, film boiling, and transition boiling. All these are implemented using user-defined function inside the Fluent code, which is a big credit of Professor Aranok Chakraborty. So you can see this work, this model validation. You can see the pressure drop inside the bed, two-phase pressure drop. These are liquid vapor pressure drop. How these are matching with the experimental data. So to see the sensitivity of different models, closure models are implemented and the sensitivity is checked inside the code. Okay, you can see. Now, how the dry out is estimated? This is done in a very in a very indigenous, basically in a very innovative way. So basically, when the bed is devoid of liquid, the alpha L is checked first. Alpha L means the liquid void fraction. Liquid void fraction is checked. Liquid void fraction is 0 and the vapor void fraction is 1. And second criteria is, if the temperature in the local level, this temperature rise occur, then we say that the bed is dry out is achieved. Now you can see here, say dry out power we have simulated in two situations. 38 kilowatt. With 38 kilowatt, you can see that the void fraction of the liquid is very less, close to 0.05. The moment we would use 38 kilowatt, we use another extra 39 kilowatt, you see this will become 0. The liquid saturation becomes 0. Now you see at the with 38 kilowatt, our temperature is almost stable. Just with addition of 1 kilowatt, 39 kilowatt, how you see the temperature in the particular area and the cell temperature goes on increasing. So 39 kilowatt is the dry out power here. That is the inference from the typical simulation. Okay. So this is wisely done, and you can see how it is achieved. You can see here this is the bed, this is the liquid and vapor, and you can see in the bed there is an accumulation of vapor here, and you can see the red patch here, accumulation of heat, and the localized rise in solid temperature. Now you see this dry out is a local phenomena. In the entire domain, in a particular situation, there is a void devoid of liquid, and there is a huge rise in temperature. So it is a localized phenomena, but this localized phenomena can be predicted by using this CFD model, and you can see the liquid vapor to the velocity profile, and under this situation you can see dry out power, how it is changing with the bed porosity. As the bed porosity is increasing, you can see the dry out power is increasing because the bed is allowing more flow to occur inside it because of the low resistance. Okay, because of the low resistance, the dry out power is increasing, and you can see here with the particle diameter, increase in particle diameter, dry out power is increasing here. Okay, if the individual debris particle diameter increases. Okay, and you can see here because of so many factors, increased permeability and decreasing interfacial area density, and the higher power requirement for vapor generation. So all these effect, increase in particle diameter increases the dry out power. Okay. Now you can see effect of bed composition. Okay, how it changes the dry out location. You see the change in particle diameter from 1 to 2, 1 to 2. You can see this is 1, this is 2, this is 1, this is 2. So when the particle diameter changes from 1 to 2, you can see the dry out location where the vapor accumulation and the temperature rise takes place. It shifts from this corner to this part. Okay. Now similarly in the porosity in the bed level, why we are doing this? Because in the bed pattern, it is a statistical process. The particle diameter may be varying, the porosity may be varying depending upon the several situations. So we have done a parametric analysis. We can see here how it influences the bed, the dry out point significantly. Okay, so change in porosity, you can see the dry out patch is changing. Okay. Now we have seen the liquid subcooling level. with increase in liquid subcooling from 0 to 20 degree, you can see the dry out power increases a huge value, 2.5 kilowatt per meter cube up to 20 kilowatt per meter cube. Okay, so this is also done. So this subcooling effect has not been done by any other researcher. So this is another contribution. So effect of coolant flooding mode, how the coolant flooding mode is changing. Okay, say there is one top flooding, one one bottom flooding here. This is the bottom flooding, and then the lateral flooding. Okay, if you keep the space. So how this is changing the dry out heat flux? So dry out heat flux is influenced like this by bed A, bed C, bed B. You can see by lateral, by the bottom injection and lateral, we have the maximum dry out limit. So the cooling effect is better and the dry out margin is better. Now you can see the dry out is a, like in the something in the, it is a safety parameter, and something like some yield point stress is used in some material science or the strength of material. It is like dry out is the limit of the debris situation or the porous bed multi-phase situation, where it is a limit. If you can increase the limit, you have a greater margin. It's like this. So we have done this analysis to get this, how much, what are the parameters which can influence dry out margin. Okay, now you can see the coolant flooding mode, how it influences. Now you can see the coolant flooding mode, top flooding mode, lateral flooding and bottom flooding, how it influences. So you can see the solid temperature, vapor accumulation, and this vapor accumulation here. Okay, so in the top flooding situation, you can see how it influences. Okay, so bed A, this is the top flooded situation. Okay, at 10 second, this is the vapor accumulation takes place here. Okay, and at 1800 second, you can see the vapor patch. Just it at 10 second it starts, and at 1800 second it goes inside the bed like this. Okay, so these are the publications of related to the debris cooling. Several publications have been done, and one book chapter is also achieved. So in this case, in this keynote address, basically we discussed about this few challenges and how step by step we solve the problem. So we can see here, if we go back to the initial slides, okay, you can see that what are the challenges and how we solved it. That big challenge is to solve this problem, this practical problem, like this debris cooling problem, and this application, fuel coolant interaction. So these are system level model. Okay, a huge problem, a complex problem. There are several parameters, several issues, but underlying principle is basically the boiling, heat transfer, heat and mass transfer, and the several issues. You can see the several issues which we have solved stepwise, and then the challenges we accepted and we try to solve this, come up with the solution. Definitely there will be more challenges involved in this complex problem, and there will be gap in research. Okay, so in currently we are doing some condensation work, and Dr. Priyankan Dotto has done a direct contact condensation, which we cannot present here because of lack of time, and Mohammad Naeem Hossain. So he is also one of the organizers of this event. He is doing some multi-phase work in the boiling heat transfer, pertinent to the natural circulation boiler, the riser tube model and the design by using the boiling heat transfer and two-phase flow. So there are several challenges and there are methodologies, and to solve a challenging or complex problem in thermal or any other area, if you stepwise think and you can go like a tree structure, you can solve stepwise. So in a modular level you can solve it, and you integrate it to a system level, then you can come up with a practical problem. Thank you very much. Thank you organizers once again, and it's a great moment for me. It's like a reunion. So thanks all for giving me the opportunity to deliver this lecture.
Thank you, sir. Thank you very much. Thank you, sir.
If you have any question, you can ask or you can continue, whatever.
Yes, yes. If anyone want to ask any question, please. Nothing, sir. I don't think anyone has got any question.
Okay.
Thank you,
Thanks.
sir. Thanks, sir. Now, Professor P.K. Dan from IIT Kharagpur will deliver his keynote speech. Professor Dan, sir,
Yeah.
please.
Good morning, everybody. I would like to thank the organizers for kindly inviting me. Um, Professor Roy of the principal of this college, Professor Panda, Professor Kundu, who took special care about the interactions and logistics, and the speakers of the day, Professor Mayor, Professor Ghosh, who has already spoken, and after me, Professor Chakraborty from my institute only. He will be here, and dignitaries and delegates, and dear colleagues and friends, ladies and gentlemen. Um, in fact, I would begin saying that the conference is practically, as I see, covers a wider aspect or several aspects in mechanical engineering, of which thermal is a major pillar, but alongside there are papers and presentations from the area of manufacturing engineering, production management, and all design related etc areas, subjects. So, what I was thinking, which I discussed once with Professor Kundu also, that what if I try and touch a topic which is uh, common to the interest of all the stakeholders or all the participants involved in this conference this today. And I am delighted to say that Professor Panda, uh, in the inaugural speech, has mentioned very categorically and meaningfully, I suppose, is that today's technology are also to be uh, India centric, that which serves the country, and that is a very important thing. We do research, and our research gets published in international forums, particularly journals, which clearly indicates that our research is definitely competitive enough. Very, very true, and that's happening for decades, and we are happy about it, although we are trying to do even better. But the main problem that remains, that in spite of all these, uh, India perhaps has not been able to address a very important concern of its people through engineering. Like, we have not been able to come out with good products or even processes, or there are not so many patents or technologies commercialized or innovated in such a way that actually it helps people. We are today so much dependent on others, other countries, that two things are happening, which is costing our economic independence, and two, which is creating um, downturn in terms of our quality of living. Because if anything, if we don't produce, cost 1,000 rupees, and if we have to import easily, if we don't have that capacity and capability, we have to pay 5,000 rupees or more maybe. So it is multiple times. That's what I intend to indicate. Now the question is that while it is true that efforts are being done, and many, I would say, activities are happening in many places. After me, Professor Suman Chakraborty will be speaking, who has done and his team has done a marvelous job of COVID app. Perhaps you have heard by now, um, which has got the ICMR approval also. But those are very, rare incidences in academic institutions. It is not very, I would say, widespread. So one or two examples will not suffice. What we really need today in our country to have many of such things. And therefore, um, the mm, the government of India now, I would say, has awakened to this problem. For last so many decades, maybe post independence and thereafter also, people never thought of developing technology here. And academicians, as we are, we were happy just doing some research and publishing in conferences and journals, but not really translating them into products, which we call innovation. Um, so the thing is that government of India now has given a call in many ways, like say Make in India, which ultimately has to translate into something called Made in India, um, Startup India, and also are boosting many of these projects through which new innovation can happen, and funds are being created, etc., etc. Unfortunately, what we see that although some funds are available here or there, not many takers are available. Neither the faculty members nor the students. At no level, there are so many takers. I'm talking in general, not from a particular institute. Maybe in some institute, maybe in IITs and IITs, the number is a little more, elsewhere it is a little less. But by and large, it is not very encouraging. So, therefore, the next question is therefore, okay, fine. And one more thing that I need to tell you, that while we are talking about innovation, um, that innovation generally were happening in the developed countries, in the developed world, where uh, the features were being improved, features were being added, products were getting over engineered, and the prices were going up, and that used to be called innovation. One simple example is that there are many cars produced in the Western world, which also were sold in a country like ours, where the speed is maximum speed available is 260 kilometer per hour. I don't know who drives at that speed, but we pay for it when we buy. So these over-engineered products with supererogatory features is practically of no use to us. And therefore, if we have to think about India-centric, or rather more widely, if we can use the term, emerging economy-centric products, like not only India, China, Brazil, I mean other countries in Latin America, Africa, and many other Asian countries, including Indonesia, where the population is quite large. And the population is so large that in many, I can go to many details. I have the PowerPoint ready with me. I can give you the country-wise breakup and all that, but that is certainly is not necessary at this stage. If I say that out of today's 7.8 billion people resides 5 billion, out of 7.8 billion people, 5 billion resides in these emerging economic countries, including all these names just I have taken. And imagine that their affordability is far too less compared to the rest of 2.8 billion people living in the Western world. Therefore, we definitely need a different kind of innovation. What that innovation is. And therefore, this was clearly identified uh, just after the last financial meltdown or crisis that's called global financial crisis happened in 2007 8 when Lehman Brothers were winded up and all those things had happened. Interestingly, I did a research, and many others also have reported similar results. That the innovation now for our kind of economy, for the emerging economy, are not supererogatory, feature oriented product development. Rather, ours would be to focus on core functionalities with reasonably and acceptable quality, reasonably good and acceptable quality, where and reliability, where we cannot compromise much. Possibly, if I have a notional yardstick saying that okay, if the world class product reliability is 100, then it cannot be anything less than 90. Preferably, it should range between 90 and 100, where the core functionalities in terms of features, one may come down by 25% or so, which drastically would reduce the cost, maybe to the half, which is the innovation pathway. Therefore, this innovation pathway is uh, based on the affordability engineering with acceptable quality, if we may define this in this way. And this is called frugal engineering. Incidentally, as I was referring to, I'll go back now to my slides because I have made the preamble. If I show you the slides, then I think it would be uh, somewhat just a minute. You're uh, present now. Um, um, Professor Kundu, are you there online?
Yes, sir.
Now the thing is that they are present now on the. I have clicked on the arrow, but normally a pop-up comes where I actually upload the file, but that I find it is coming as your entire screen
Sir, actually,
or a window, a tab.
actually, sir, from the previous presentation also, there is some problem of uh, adding some PPT here. So there is some technical problem, I think, from the Google Meet also. I don't
So what do
know
I do? What do I
be.
do now? Should I only speak or should I send my PPTs to you so that you can show? Huh?
You send it to us.
Okay, I'll do that. But in the
We
meantime,
will show it.
okay, fine. Okay, I mean, this is the problem that I'm encountering, and I understand the previous speaker also faced that. Just quickly. Okay, okay. I'll just send here. Yeah, just quickly. Sorry for the interruption, but it is not in my control. Just one moment. I'll just attach this. I'm not writing anything. I'm just sending, right? Okay, okay, okay. All right. You have to kindly allow a couple of minutes, please, because I need to send it. Just few seconds more. It is opening, so I'm sure.
Is there any problem, sir? The video streaming has stopped. ফোন করে নেবো নাকি এখান থেকে ফোন করে যাবে ফোন করে নেবো কোনো জন্য
Hello, am I audible? And is everything fine out there? Can you see everything? Can you hear me?
Yes, sir.
Okay, thank you so much.
Audible now, sir.
Yeah,
Please
yeah, fine, fine, fine.
continue.
All right, all right. Okay. Kindly let me know, Professor Kundo, how long, how much time do I have? I mean, because we are
Sir,
running late, so I would
as
like
much
to.
as possible, as quickly as possible, you can conclude, sir.
Okay, all right, fine. I
Okay, sir.
have
Okay,
my this
okay,
thing
sir.
because it is already late, and I
Yes,
have
sir.
another meeting to attend also. So, would it be fine if I close by 12:30?
Yes, sir. No, no, sir. Actually, time is already late by half an hour.
All right. So what I'll do is I will not show the PPT. I will speak
Yes,
and
sir.
close. Fine, fine.
Yes,
All
sir.
right.
Yes, sir.
All
Yes, sir.
right.
Yes,
Good.
sir. Yes.
Okay,
Yes.
fine. All right.
Hello.
So what I was telling that if we did a quick research and found from there that the number of articles, if just if we go to the Google Scholar citation, Google Scholar, we would find that the number of articles that was published in 2009 on frugal innovation or frugal engineering were just 40. The same has gone up in 2019 as 640. That means a 16 times increase. So, Professor Kundu, just can you quickly raise the slides quickly in a few minutes? I would just ask you to hold at some point.
Yes, yes,
Uh,
sir. Yes, sir.
yeah,
Yes, sir. Yes,
please,
sir.
please go ahead.
Okay,
Please
okay,
go ahead.
okay, okay.
But quickly change because I will not touch. Okay, I have already discussed that 7.5 billion, 8 billion. I am not going to. Okay, just hold on for a while. This is a
Okay,
model
okay, sir. Okay, sir. Okay,
which
sir.
is
Okay,
important, that there
okay,
are
sir.
two aspects to frugal innovation. One is that frugal engineering and other is need based ideation. The point that I want to harp on this model is that many of the frugal engineering, frugal innovation products, which are actually developed in the lead market, that is the lead market like India, where the product is developed, tested, tried, sold, established, then that is exported or moved to the Western world. There are many such examples which are called reverse innovation. As at the beginning, I said that normally the innovation happens in the Western world or developed world and it comes to the emerging economic countries, which is called trickle down process. Here, instead, it becomes a trickle up phenomenon. That means that whatever is developed here is exported there. There are several examples of this. I can cite one, say, for example, General Electric produced that Mac 400 echocardiogram machine. Siemens, I'll show you that example. So there will be plenty. The point again that I would like to touch is that there are so many companies in the world today are working based on frugal engineering and frugal innovation ideas and concepts. Um, One good example, maybe, say, if we take the automotive areas, the term frugal engineering was coined by none other than the CEO of Renault Nissan, that is Carlos Ghosn, who actually coined the term frugal engineering in 2006, being inspired by the concept of Tata Nano. When the Tata Nano project was given to them, the term was coined, and based on that philosophy, though it may be pointed out here, though Tata Nano here, for various reasons, I'm not going into the detail. There are debatable issues also, but though Tata Nano has not done well here, but the idea has not died. That idea has been adopted by the automakers elsewhere. Example is Quid, example is Logan, where Carlos Ghosn himself led those projects. And the frugality was brought in, and low cost cars came out, and it got huge market worldwide. So I, I think we are seeing some other screen, Professor Kundu. I mean, okay, yeah. So that is a reverse innovation is a trickle up process. So just I wanted to tell you that. Kindly go up the screens quickly so that I can. Please, please, Please change the screens. I mean, I would skip all the definitions, everything. I will just go to. Acha, they okay, okay. Just skip that. I just wanted to see you. Uh, uh, just bring that slide back. Just which is past that worldwide the universities are concerned with innovation and all. Just no, a slide before yeah, just keep it there. There are so many top universities in the world, starting from Stanford, MIT, Harvard, just name it, they are there, who have introduced the frugal concept or innovation concept. And there are frugal concepts also, like say University of Hamburg, University of Fraunhofer, University of Santa Clara, and many more. And the person, the Professor Mayer, he is from South Africa. In fact, in South Africa, on mobility, a huge work is on regarding frugal engineering. So these are some of the work. I mean, okay, please move on. I just would close with some examples, so that instead of going to theories, that theories can be discussed later, some other time, some other forum. But please keep all that. I would like to finish because I also have some other thing. I'm getting late, so go to the examples. Some of the examples, the GE example. Okay, these are the entrepreneurship about. These are all reverse innovation. I have just touched the point. Please skip. I have already discussed that. Carlos gone and all. Please keep that. Please keep that. Okay, the business is $6 trillion worldwide on frugal. That's very important. The volume of business is huge, $6 trillion, of which India alone is $1 trillion. That's therefore the innovation, etc. If can be done, it has a huge market. Please proceed. Okay, but I just would come to this where the engineers are interested and should be interested and are concerned, irrespective of discipline, irrespective of domain, rather, in mechanical engineering. It may be thermal, it may be manufacturing, it may be any design or whatever. So there are certain things common, that is called design thinking. The design thinking is cuts across the domains and disciplines. In fact, it cuts across disciplines. And thereafter followed by the engineering design process support. So I just would quickly touch on this. Please go to the next slide. In this presentation, you please treat as a very introductory one. If you are interested, then we can have a different discussion later. But the frugal design thinking, which are of course, you hear the Prime Minister every other day talks about local, etc. But there it is a feature that it has to be done locally. It should be affordable, manufacturable, functional, sustainable, and user-centric. And that's the design approach. The modern or emerging design approach. That's what I mean for our kind of economy. Please proceed. Please proceed. Please proceed. Okay, the definition I would skip just now. Yeah, that is the example I was talking about. This is the example of Mac 400 ECG machine, which costs. Go to the next slide, then I will show you that it costs 1/10 of the price. Just go to the next slide, please. Which costs otherwise, say the full-fledged equipment that originally was developed now cost $10,000, vis-a-vis the one on the right. You can see that which is being used in our country now, and more importantly, it is a reverse innovation. This has also been exported to countries in the West, and they are using it for their emergency purposes. So that's a great example of reverse innovation also, where the features have been lessened. The printer, so for example, in this computer printer is this printer here is the bus ticket printer is attached to this bus ticket. The printing and the bus ticket and the depots are just fitted. So you understand how frugally, but without compromising the output quality, because whatever is to be legible, that is legible. Yeah, please go to the next slide. This is another example of mechanical engineering, that CMRI has developed a tractor which is a very low cost one, and there are many small plots which require a low cost tractor, but many farmers, etc., cannot afford. But this solves that problem. They have come out with a very low cost tractor, and that serves the purpose, which is called Krishi Shakti. And its CAGR, that is cumulative growth rate, is also reasonably good, more than 3% per year. So that is good. Next, please. Tata Nano, of course, is a big example. I mean, this idea has not died, though Tata Nano has not done particularly well. But I'm quite sure that this knowledge is not lost. This knowledge will be fetched and dug up in some place. And like Quid and Logan, many other car companies would be using that philosophy and would be producing many more. Yeah, please, please. Okay, this is another example of Siemens. Siemens, for example, I'll tell you, they have a portfolio called Smart, where they actually are focusing on the affordable category of products without compromising on quality to a great extent. So this is one example, which costs nearly one third of the cost of the original or the elaborate equipment that is for X-ray machine. Go to the next, then I will talk about Smart. Please, next slide. Next slide, please. Yeah, this is Smart. Actually, Smart, they have defined this as simple, maintenance friendly, affordable, reliable, and timely to market. So the products are normally half of the price, at 50% cheaper. Incidentally, one may need to know that this market for this portfolio worldwide per year is 200 billion US dollar. So you can understand how large the market is. And therefore, if our innovators, our engineers, our students, our faculty members are working on this, there is a huge scope, be it from any discipline, be it from thermal, fluidics, etc. Lot many manufacturing systems, design, whatnot. In fact, today, no engineering is complete by itself alone. It needs the support of other, I say, the interfaces and domains, and is a fusion, in fact, and not only related to mechanical engineering. Even now, look at the car today, it is not a mechanical engineering product anymore exclusively. It is an interdisciplinary product, so multidisciplinary product, so transdisciplinary product. So all these things are coming into here. And so obviously we are talking about mechatronics, we are talking about robotics. It is not only now those have been wrapped up in the mechanical engineering domain. That's quite true, but they are in the interface. So that is actually the solution engineering. Let us talk about in that fashion. Please go to the next. Interdisciplinary engineering or transdisciplinary engineering. Next, please. Next. Okay, this is an example of Jaipur leg, which is a low cost thing again, which is a foot and leg replacement, and done is at very low cost, which is an Indian marvel. In fact, Stanford has come to look into it and doing business promotion on this Jaipur foot and Jaipur leg, which is extremely affordable, 1/10 of the price that normally would be charged by the original manufacturers. Please, next. Next, please. Next, please. It is a Stanford invention. I just would summarize this. I would not go into all the details because there are four important things to be kept in mind while designing something frugally. One is the reduced cost of ownership. That means total cost. That not only upfront price point, but also the maintenance cost all through its I would say installation. All costs associated with should be low. That is total ownership cost. Then it should be robust. That means it should be able to, please next slide, robust, which should be able to, in all possible variable conditions, like say extreme heat, hot condition, extreme cold condition, and yeah. So please next slide, please. I mean that thing is in the next slide. Yeah, so robustness, which should be able to accommodate all these variations. Next, please. Which is again the user friendliness, and finally the economy of scale. It should be user friendly and easy to use and fault resistant. Economies of scale is very important here. Just one thing to be remembered is, although people say frugal engineering is a new approach and concept emerging, I don't really personally think that it is completely new, although its impact is new, or impetus is new. But if we go back to Henry Ford's time, I cannot say that it was not frugal in some sense, where it was actually uh, economy of scale, a large scale production, whereby the cost per unit could be brought down to a great extent. So here the profit is less per unit, but the volume makes it up for it, and the total revenue is high, and margin or profit is also high. Please next. Also, it brings us to design thinking. These are the reports that why design thinking is so important. I would skip. I would just say design thinking is so very important. Please go to the next slide where we, yeah, just one important thing that we need to really touch up. Um, the three things when intersect at a point that actually becomes the innovation goal. Three things. One is it has to be technically feasible. It has to be economically viable, but again, it has to be ultimately be used by the consumer or the purchaser. So it has to have the desirability. So it should be desirable. So it is that intersection where the three aspects meet. Next slide, please. Acha, this is one important thing. Maybe you can just look at it later, but these are very important thing that Tim Brown of IDEO has proposed, and it originated at Stanford. This concept, the design thinking process, which are having uh, 5 steps. Empathize, that is means what the user actually needs, the requirement analysis kind of thing. Empathize, define the problem, ideate, develop the prototype, and test in the market, that is. So and then it is not a linear model, it is a back and forth, so it is iterative model. So therefore there's so many arrows, but therefore these are the steps which would help in reaching the final goal through the design process. Next, please. I just okay, the engineering design process I'll skip because I have taken the Abbott, that USA board of engineering and technology. They have defined engineering design process. I will skip that. It is an academic aspect that I wanted to discuss. Yeah, this is what the NASA's best engineering design model they have produced. What are the steps which the graduate students or even postgraduate students can follow, and for them, and so I mean follow means that is the design process they have developed it for, but it is a generic approach now. So please go to the next slide, and then I will just mention the steps, which means the steps are the 6 steps. Ask, that is to identify the need, which is to be done very correctly. If the need identification is wrong, the whole lot of effort will go waste and everything will be wrong. Then to develop possible solution, that's called imagine. Then to decide the best course to plan. Then to develop the prototype, test a model, that's create. Then to evaluate the prototype, etc., is called test. And then finally improve. That is the purpose. Please go to the next, and I will skip all this because those are the examples and elaborations. If I had time, I would have shown you, but these are the explanation. Please skip quite a few slides which actually explain this, which I have quickly summarized here. Professor Kundu, please, can you raise those slides to come to the last one? So these are the steps which I actually elaborated. I have, okay, just here, just on the left bottom corner, you see that the imagination basically is a divergent convergent thinking. That is, first we create more alternatives, and then we narrow down from those alternatives to select few. And therefore there are 2 phases. One is the problem phase, that is a divergent convergent, converge on the problem, right problem, then again solution. We work out different possible alternatives and then converge to one final one which is most effective. So this is a divergent convergent thinking. Please keep rest of the slides till the next slide, the last slide. Please go there. I will skip many. Please keep. These are the explanations of what I have already said. Those are the elaborations. Those are nothing but elaborations, pictorial elaborations I had in mind to show. But okay, you can skip that. This is the Make in India and Atmanirbhar Bharat. For all this is necessary. Skip that. I have already said in my preamble. Yeah, this is one interesting case that I, because of this frugal innovation, our student at IIT Kharagpur has developed 2 robots, and they are working in one COVID hospital in Jharkhand. And I mean, so you can understand that low-cost things are also very useful and helpful in crisis situation as well. Go to the next slide, please. That this is to say government is providing several these things. I have already said this medtech research parks, and then the MSME help, etc. Please keep, because those are some funding opportunities, etc. Yes, MSMEs, they are trying to boost all that. Yeah, this is my last slide. I just would like to tell you, to close my session today, that frugal. In fact, we are very good in frugal, because see, if we talk about the MOM, frugal MOM, that ISRO's um, Mars orbiter mission, which got attention of the entire world, where it has been produced at nearly 1/10 of the cost of MAVEN, that was NASA's launcher. And the concept was that it didn't slingshot to Mars directly, but it moved around the Earth. It orbited for a month and then shoot out, and that helped to reduce the cost to a great extent. So, and most importantly, while it was so cost effective, the quality was superb, which was supposed to work only for 6 months. That actually, even as I am speaking with you now, it is still orbiting up there around Mars. And from the report we get, it will continue to do so for some more time. Thank you very much.
Thank you, sir. Thank you very much, sir.
If there is any question, fine. Otherwise, we can have a session later. Thank you.
Okay, sir. Thank you very much, sir. So now, Professor Suman Chakraborty will present his plenary speech. Yes, sir. Sir.
So thank you so much. Let me try to upload my presentation, and
yes, sir.
So it's always difficult to upload it. Let me try it, and then I will go forward. So it is a very similar problem as Professor Dan was facing. This uploading in Google Meet. So I mean, I am trying it out in several ways. It actually gets resolved with a few tries. So I will just log out and log in.
You can send your PPT, sir, to us. You can send your PPT to us, sir.
No, I mean, because it has certain images, the uploading may be difficult. So I will try, and in a few attempts it will be possible. So just be patient. I may leave the call and join.
Okay, sir, no problem.
I may leave and join just to make sure that somehow.
Okay, sir, no problem. একদম শুরু করতেই হবে। ওখানে ছটা লোকের জন্য, 6-7টা লোকের জন্য কিচ্ছু আসবে না, এখানে কিচ্ছু আসবে না। বাকি লোকেরা জান থাকবে এখানে। ছাড়ো, কোনো সেশন শুরু করতেই হবে, নাহলে লেট করলে মুশকিল।
So I hope that the presentation is visible. Just one of you please confirm.
Yes, sir. The presentation is audible.
It is visible, right?
Yes, sir. It is visible.
Okay. Okay. So I will make it full screen and start presenting.
Okay, sir. Okay, sir.
So this is essentially something that continues with the talk of Professor Dan that was going on prior to my presentation, and it continues with frugal innovations, which are very much intrinsic not just to the mechanical engineering research in the modern era, including but not limited to thermal sciences and engineering, fluid mechanics, manufacturing, etc., but also the other interdisciplinary perspectives to bring in very advanced technologies towards the ambit of frugal innovations. In more specific terms, I will talk about some examples which are related to affordable diagnostic technologies. The objective is to bring in advanced diagnostic technologies from the lab to the field. What we will be discussing about is, of course, very much relevant to the present COVID era, but also beyond that. So the deep-rooted need for such innovations in the healthcare domain is based on the fact that summarily all the major healthcare amenities and facilities, including the numbers of hospital units, hospital beds, diagnostic labs, etc., they are primarily centered around the cities. The rural scenario, which is deprived of these facilities, the people there are the worst sufferers. And although we talk of many reasons because of such suffering, including shortages of doctors, nurses, other factors, we often pinpoint the importance of technology. To overcome these barriers, there is a current endeavor to develop units which are digital health initiatives similar to ATMs for money banking. This is a brick and mortar small unit called as health kiosk, where the patient approaches the frontline health worker, talks about the problems. The frontline health worker translates that in the form of a software interface, which by internet is connected to the doctor sitting in the big city. The doctor gives recommendation, but the major challenge is that when the recommendation comes in the form of diagnostic tests, it is extremely challenging because of either the cost or the non-availability of proper infrastructure, as well as some other technical bottlenecks to perform those diagnostic tests on the patient. This requires certain disruptive innovations, which is very much a frugal innovation, but sometimes it may also demand a very high-end scientific innovation, considering the fact that the power supply in the field where these diagnostic tests are being implemented, the power supply is either not available or erratic or of poor quality. The environment is hot, dusty, humid. The reagent storage is not well supported by proper refrigeration units. The supply chain of reagents doesn't exist. Trained technicians are not abundantly available, and there is extreme price sensitivity. While these facts remain, the problem is further compounded by certain myths, beliefs about the diagnostic tests. There is no clear understanding whether a particular diagnostic test is screening or confirmatory in nature, whether the cost of the kit and the cost of the test, they are synonymous, whether a cheaper diagnostic test gives a better quality diagnostic solution, whether a more rapid test is welcome. If the test is dealing with reagents, whether in an effort to frugalize it, there is a chance of contamination of reagents that will spoil the test. Are the reagents stable? Is there any cross reactivity of reagents which can lead to false positive results? Is the test resource intensive? Is the test user friendly so that unskilled operators can also operate the procedure? Is it reasonably accurate, which is benchmarked by two important terminologies in the diagnostic world: sensitivity, that is the ability to detect true positive, and specificity, that is the ability to detect true negative. Is the electronics unnecessary, fancy, or is there an indirect sensing which is used, which compromises with the gold standard procedure? These are questions which are not commonly known or not commonly addressed when a new path-breaking technology attempts to invade the market and is publicized in the media. The primary concept on which I will give a few examples, and because the platform is not specialized in this particular area, I will be broadly generic. So it is about diagnostics with 1 drop of body fluid at the point of care. So what this innovation tends to look for is 1 drop of body fluid is collected, maybe finger pricking of blood as an example. The body fluid is dispensed in a paper strip where there are other reagents with which there are reactions which can give a colorimetric signal, and the signal is captured either in a small portable electronic unit or by a smartphone unit. They are analyzed typically either in a smartphone altogether or by internet interface between the smartphone and a centralized computing unit, and the results are disseminated in the smartphone. These are simple portable technologies, easy to handle. It is possible to manufacture such devices in large quantities. The tests are designed to be inexpensive with very minimal infrastructure required. These are designed to be rapid tests, and if necessary, they can be automated partially. Full automation will increase the cost, but at least to a partial extent, they can be automated. One important aspect of all these diagnostic tests is manufacturing. So to make microchannels on a piece of paper for disease diagnostics, which in the paper microfluidics world is known as MUPAD or micro paper-based analytical devices, we need to direct the body fluid from the source of collection to the destination where the reaction will take place. And this is guided by microfluidic channels, and that guidance has to be assured by printing microchannels on paper. So we have developed a very simple inkjet printing based procedure where the design of the microchannel is printed on the paper, which is a special quality paper, and it is heated for 4 to 5 minutes at around 200 degrees centigrade, so that the toner particles which have come from the printer, they will melt and block the pores, so that this black colored structure, which is the hydrophobic barrier, is created, and the body fluid flows from the source to the destination by capillary action in the paper pores, so that there is no pumping which is required. If the manufacturing is done in this principle, then it doesn't need a mask, which is commonly needed for microfabrication, and only a printer and a hot plate is good enough, and no equipment is required. The technology can be further advanced by making pencil sketches on a piece of paper. This is again a frugal innovation, but it can be automated in a upscaled manufacturing platform by embedding graphite particles, which can come from pencil sketch by manual manufacturing, but it can come via automated dispensing also by graphite particles, which form electrodes, and if you apply electric field, the fluid flow can be further manipulated by electric field. This conceptually is known as paper and pencil microfluidics, where the paper and pencil microfluidics is essentially a combination of the paper microfluidics with pencil sketched electrodes. With these kinds of microfluidic strips on paper, it is possible to make certain basic detections which are very, very important and common in public health. The first example that I will talk about is the blood glucose detection on a printed paper strip. There are several glucometers available in the market which do the similar work, but the challenge is either the cost per test is beyond the critical limit. Even if it is 30 rupees, 40 rupees, people in the rural scenario, they are not in a position to afford that kind of a test on a regular basis, because for many people that monitoring has to be done very frequently. The other challenge is that in many of those devices, the whole blood diagnostics is done, and in that way the glucose of the whole blood is examined rather than the glucose in the plasma. The plasma glucose is the clinically relevant parameter for medical intervention, but the challenge is that if you want to do it in a microfluidic strip, you have to first separate the plasma from the whole blood and then do the analysis. The plasma which is there in the blood, to separate the plasma from the whole blood, you require a special technology which in a big lab is done by centrifuge procedure. In a microfluidic platform also it can be done, but it requires a special microfluidic design which makes the channel fabrication complicated. What we have done here is that we have integrated the plasma separation and the glucose detection by the classical gold standard procedure in a single step process in a paper strip, in which 1 drop of blood is loaded after finger pricking, and there is a color developed in the reaction pad which tells what is the level of the plasma glucose. This entire thing is done by interfacing the paper strip with a portable readout unit in the same way in which a credit card interfaces with a credit card reader. The entire analysis is done in a smartphone so that no additional instrumentation is required. Similar diagnostic procedures have been developed for hemoglobin level detection. The reaction steps are somewhat more involved, but summarily the procedure in terms of implementation is very similar, that you prick the finger, take 1 drop of blood, load it on the paper strip and observe the colorimetric change by a smartphone analyzer and disseminate the result on a smartphone. Going further from the very routine blood glucose or hemoglobin tests, we could also advance the paper microfluidics technology for assessing antibiotic resistance. There are many diseases for which antibiotic treatment is required to save the life and to arrest the infection. However, all antibiotics do not work all the time because of several reasons. Certain patients have resistance to antibiotics, in the sense that the bacteria out of some particular infection will not die even if that antibiotic is given. So how do we assess this antibiotic resistance? So this is an example where if there is an urinary tract infection with E. coli, so that bacterial sample is isolated. This is a 3-dimensional paper microfluidic platform patented by our group. So you dispense that in a microfluidic unit where there are 4 layers. In layer 1, there is a colored chemical called as chromogen, which is blue color. In layer 2, there is antibiotic. The antibiotic which you want to study and see whether it will work on the patient or not, who is identified with a urinary tract infection. In layer 3, there is the bacterial suspension, in this case E. coli. So when you bring these layers together, the antibiotic comes in contact with the bacterial solution, and if the bacteria is killed by the antibiotic, the color of the chromogen will start changing from blue to pink. The fractional change from bluish to pinkish will give an indicator of what is the fraction of the bacteria which is killed by the antibiotic. So in this way, the doctor sitting in the chamber can assess the antibiotic resistance of different antibiotic drugs and give the patient the appropriate antibiotic drug which will kill the bacteria. From bacteria, we come to viral infections, which is the need of the present hour as the entire world is going through the COVID-19 pandemic. The virus typical to the SARS-CoV-2, which in common terms we call as COVID-19, is hallmarked by its RNA, which is a genetic material. So if you look at the structure of the virus, you have the inner core where this genetic material is there, and the outer periphery where different types of proteins are there. So the diagnostic test can either target these proteins, which are called as rapid antigen tests, but more fundamentally, the diagnostic test can also target the RNA, which is considered to be the gold standard technique for detecting the viral infection, because the RNA contains the fundamental signature of the virus. The gold standard RNA-based diagnostic testing is based on a principle known as RT-PCR technique, which is summarily the reverse transcription where the RNA is converted to DNA. This is required because the DNA can be amplified to large number of copies, but the RNA cannot be amplified. So you can increase the concentration of the signal that you want to detect by amplifying the DNA, and that is why you convert first the RNA to the DNA. This is called as reverse transcription followed by amplification. This amplification in heat transfer technology is commonly done by cyclic heating and deheating process. So this thermal cycling is the hallmark of the PCR machine or polymerase chain reaction machine. So in this way, copies of the DNA are produced. This means that to monitor this RNA to DNA and amplification of DNA and detection of DNA, we need a machine which can perform this task, which is known as the real-time PCR machine. Despite being a gold standard advanced technology acceptable all around the globe, it is limited by the consideration that these machines are expensive, resource intensive, and need highly trained technicians to undertake the test. There are simplified technologies where the RNA extraction can be done, the amplification of the reverse transcripted DNA, that also can be done. The simplified technology, instead of using the thermal cycling, uses isothermal procedures. The challenge is that there is no universally standardized machine which can perform these isothermal nucleic acid tests. There are certain high-end machines which can do that, but they are very expensive. The low-end tests commonly use certain isolated heat blocks instead of having a customizable machine to do the test. What our research group intended to do is two things. One is, whatever such tests are available for isothermal nucleic acid based detection of COVID-19, typically the RT lamp based procedures, we wanted to improve upon that so that the detection is more specific. And what it means in common terms is that it is possible to specifically detect COVID-19 as compared to other infections which could be of similar nature. So to do that, we had innovated a special step, but all these can be done in an isothermal or piecewise isothermal nucleic acid based tests. So this procedure and the portable device where we can generically perform arbitrary piecewise isothermal nucleic acid based tests, this was summarily reported in this patent disclosure which I am mentioning here. The entire objective of this patent disclosure was to come up with a nucleic acid based test which has high sensitivity, high specificity, but can be implemented in a low resource setting outside high-end molecular diagnostic labs. So this example shows that even if there are 10 copies of the virus, we can detect it. You can see that paper strip here where there is a control line. It shows that the paper microfluidic strip is working for doing the diagnostics, and the test line where if a line is appearing, that means it is COVID positive. If the line is not appearing, it is COVID negative. So we can see that even with 10 copies of the virus, it is possible to detect using this technology, and we can very clearly distinguish between influenza A and COVID-19 infection in a way that in a sample where there is influenza negative but COVID positive, it is possible to detect it specifically. The quality of any pudding or the taste of any pudding comes when it comes in terms of the eating. The quality of performance of any medical device can be assessed only when it is subjected to trials with patient samples. So with the help of the ICMR NICED, who was authorized to do the testing on our method and device, it was reported that with 200 patient samples provided by them and the entire test being performed at the ICMR NICED located at Kolkata, our method and machine for all ranges of viral loads which are told as, which are summarily mentioned as CT value in the RT-PCR terminology. The CT value is the cycle threshold value. That means after how many numbers of thermal cycles in the RT-PCR test the virus is detectable. Low CT value means the viral load is so heavy that only with a few number of cycles the disease can be detected. High CT value means actually the viral load is low. So with all ranges of CT values till around the CT value of 35 or so, our test could reproduce the results of the RT-PCR test performed by them quite satisfactorily with a sensitivity of around 94% and specificity close to 98%, taking a cutoff of CT value of 30. That means this is typically representing an infectious condition where the infection is considered to be important and critical from a clinical viewpoint. Our COVIRAP innovation, it shows 98.86% of sensitivity when validated with patient sample. So this COVIRAP as a device, COVIRAP as a method is a paradigm shift. Why it's a paradigm shift is because it is not just COVID, but it's a generic platform where a large number of tests can be performed in the similar structure at an affordable price. It includes large number of viruses, bacterial infections, parasitic infections, vector-borne diseases like typical mosquito-borne diseases, and I have just mentioned an indicative list. The reason of this mentioning is today it is COVID-19, but it will not be that imperative with the vaccination being more effective and disseminated all around the globe over the coming year or so. But there are so many other infections which are there, which will remain, and new infections will emerge, but all these can be addressed with the help of this technology. The technologies that I have mentioned so far are based on body fluids. I will try to conclude with one technology which, rather than being body fluid dependent, is body signal dependent. Oral cancer is a curse in the rural community. It is often triggered by lifestyle factors, typically tobacco chewing, and the current methods of diagnostics, they require sophisticated lab-based procedures. What it means is that large number of rural people do not actually fall under the ambit of the gold standard diagnostic technologies, not only for oral cancer, but a very important stage which is called as oral pre-cancer. It is not cancer, but a prelude to cancer, and that pre-cancer stage, if proper intervention is made, this deadly cancer can be prevented. So our research group has developed a simple handheld device which is actually a thermofluid based detection principle premised device. What it does is, it from the thermal imaging of the oral cavity, it calculates by an inverse computational fluid mechanics and heat transfer the blood flow rate in the tissue. So by doing that inverse calculation and calculating the blood flow rate of the tissue and subsequent analytical procedure, it gives a recommendation of possible screening of oral pre-cancer, cancer in different stages. We did successfully phase 1 clinical trial with this device in collaboration with the Guru Nanak Institute of Dental Sciences. and with 60 patients, this real clinical trial was conducted, and when compared with the biopsy reports and other advanced imaging reports, this exhibited around 97% accuracy in terms of the prediction, which is quite promising. This typically considering that this is intended as a screening device and not really a gold standard device or a gold standard procedure like biopsy. An early prototype has been developed and it is ready to be deployed in the field by minor sophistication and automation. This method can be extended to other forms of cancer. For skin cancer, this is already established. For cervical cancer, it is being adapted with the help of other medical collaborators. So, what we are looking for is a chain of innovations which can bring in high technology diagnostic procedures from advanced labs to common people. We commonly perform field studies for doing these procedures, and I will try to run a movie to show one glimpse of such event. I hope this movie is visible to all participants. So this is a village known as Barra in district Birbhum, West Bengal. A majority of this population whom we are talking about, these are deprived of basic facilities in terms of healthcare. So they are being treated by specialized doctors. In this case, Dr. Shatadal Saha, and they are being diagnosed by using our diagnostic devices in a primary school, which we made use of. So the frontline rural healthcare workers, along with my own students, they are doing the diagnostic procedure for glucose and hemoglobin. This is a high-end device known as HemoQ, which is available in the market at a very high price for doing point-of-care hemoglobin test. We wanted to compare the results from our diagnostic procedures with the results from these advanced devices. So this is how the method looks. So you have a team who are taking the finger pricked blood, loading in the device. This is the blood, this is the paper diagnostic strip that I was talking about. The blood is dispensed on this. It is inserted into the machine, which is the portable unit, studied in the smartphone analytics procedure, and the result is disseminated. These are compared for large numbers of patients with the results from more standardized machines for glucose and hemoglobin detection. The results were very promising out of all the field trials, and what is expected is that these kinds of advancements are going to bring in high-end technologies for the benefit of common people. So summarily, from lab to extreme point of care, where neither high-end facilities nor expert technicians are available. Our institute has developed several such technologies and is open for transfer of technology, commercialization for rapid dissemination with the help of government support. I would like to acknowledge several organizations, including IIT Kharagpur, the Ministry of Education, DSIR, Ministry of Electronics and Information Technology, IIT Foundation USA, Royal Academy of Engineering UK, ICMR, the Department of Science and Technology, Government of India, and several other friends, our teammates. It is very difficult to name each and every one of them, but I have listed them here, starting from professors to senior researchers to PhD students to undergraduate students. They have all contributed significantly towards this endeavor so that high-end, low-cost technologies can be brought to the benefit of common people. Thank you very much for your attention, and I'd be happy to take a few questions.
Hello, sir. Hello.
Yes, yes.
Hello, sir. Hormonal level testing is possible. Hormonal level, what is the TSH?
Yes, yes.
Any other?
T3, T4, TSH, all these can be done. Actually, the engineering platform is very similar, but any diagnostic, it has either a chemical or an imaging protocol and a device protocol or a device procedure. So device-based procedure is very similar, but the chemical protocol for biochemistry is very different for every test. So there are protocols for these T3, T4, TSH. We have not yet standardized those in these platforms, but this technology that I have presented, in technology world, it is known as platform technology, in a sense that it is generic, and every test of this kind can be adapted to this platform with standardization and validation.
Okay, thank you, sir.
Okay, sir. Any question from anyone else? No, sir. I think there is nothing.
Okay,
else.
so thank you so much for patiently listening to this talk, and all the best for this conference. And goodbye for now.
Thank you very much, sir. Thank you very much.
Okay.
Okay, sir. Thank you. Thank you. So, by this, we conclude our first session, the introductory session. And now, actually, all the technical sessions for the first part already has been started from 2:30. So, you can join those technical sessions. And now for that, we are closing that session. Thank you. Thank you very much, everyone.